Breaking mass news, mathematicians have finally built a tetrahedron just months ago that they've been theorizing about for over 60 years. To find out more about it, I tried to build my own, fairly unsuccessfully, and, of course, we spoke to an expert in the mass field. I mean, an actual mass field. For some reason, Matt wanted to film outside for this video, despite being constantly blinded by the sun. In 1966, mathematicians Conway and Guy theorized that both there is a tetrahedron out there which is only stable on two of its faces, but there is no tetrahedron that's stable on one face. And half of that was answered the very next year when Hungarian mathematician Hepsz came up with this tetrahedron. Also, this video brought to you by Bambu Lab printers. Yes, all the models in this video were made on my Bambu Lab X1C printer, an incredibly versatile and reliable 3D printer. So if I get this convenient and now perfectly level surface here, there are two surfaces on the tetrahedron, that one and that one, where it's completely stable. However, if I try to balance it anywhere on the other two, if I try this one here, and this is not the wind, ready? Falls over. And if I try this one here, falls over. And quite interestingly, that second one, when I balance it on that face, it doesn't fall directly over, it actually goes to the other unstable first, and then over. So if I balance it there, fall. So this is, I guess, a bistable tetrahedron. And in their paper, Hepsz defined it with its coordinates of the corners plus or minus epsilon. Here's the 1967 paper by Hepsz, and you can see there's just the four coordinates right there with a minus epsilon to define where vertex A is. Now the rest of the paper is Hepsz showing where the center of mass moves based on the value of epsilon, but I wanted to see this thing, and so I actually just took these coordinates, I assumed an epsilon of 0.1, and I made this STL file just to finding the four faces of the tetrahedron. That's what I 3D printed, and that's okay. But to get a better sense of it, my friend Sam put the coordinates into a GeoGebra file. So there's the tetrahedron, there's the center of mass, and there's where it projects down. And if I turn on the vertex labels, they're the ones as defined by Hepsz, and the face labels, we just give each one the letter of whatever vertex is opposite. And you can see initially the center of mass is directly above that edge, and that's why we have epsilon to move vertex A around. So if we move it this way, look at that, you can see now the center of mass is moved out. It's off the base, which means this is now unstable. It's going to tip over from this, face D is going to lift up, and face A is going to slam down. But where's the center of mass now? Oh, look at that. Still just a little bit out. We can move it around more by adjusting epsilon, but as long as it's not on the base, we'll start to tip, and face A will lift up, and face C will slam down, boosh. Now, this is a big face. The center of mass is directly, look at it, is just above the face. That is not going anywhere. So to recap, face D was unstable. It will always transition from there to face A. That's also unstable. It will transition to face C. Face C is stable. Now face B, if we start there, it's just stable. So there are two stable faces. It's a bistable tetrahedron. So 1967, we know a two-stable arrangement tetrahedron is possible. But what about the monostable tetrahedron with a single face it always ends up on? Well, we can't talk about monostable shapes that always end up in the same orientation, no matter how you put them down, without talking about the Gombok. I haven't got a Gombok. Oh, Steve Mould. Steve Mould has a Gombok. Oh, I could ask him to show it to me. The one time I go somewhere nice to film, and now I'm going to go inside, phone Steve. Steve, you own a Gombok.
I do. Funnily enough, I have it right here on my desk.
Oh, that's convenient.
Yeah. So look, the thing about the Gombok is it's got two equilibria, but one is unstable, and so it's only got one stable equilibrium, which means it doesn't matter how you place it on the table, it's always going to end up rolling back to this position. So that's the stable equilibrium position. There's an unstable one, right? If you put it like that on the edge, it'll balance there, but as soon as you give it any kind of knock, it'll end up back in that position.
So how does this differ from just like a weighted sphere that would always end up the same way?
So the difference is, this is homogeneous throughout, so the density is the same all the way through. So you could do it like a Weeble. A Weeble wobbles, but it won't fall down. Just to give you the. So whereas this, it can achieve the same thing. It's a Weeble, except that it's not weighted inside anywhere. This is the only object that does that. But I mean, I'm not a maths guy. I don't know. Like it's interesting that it's curved. Do you think it would be possible if to do it with a shape that's all flat sides?
It's not. It was proven in 1969 you cannot have a monostable tetrahedron. Question answered. In fact, even in higher dimensions, so a higher dimensional tetrahedron is called a simplex, all the way up to 8D, there are no monostable simplexes. It's all over. For shapes that have a delicious homogeneous filling, like the Gombok. But if instead of a homogeneous filling, if the weight was unevenly distributed, suddenly it is possible. And apparently, we believe, in 1984, John Conway, had a sketched out sort of proof that it would be possible to make a non-homogeneous monostable tetrahedron. Richard Guy had a conversation about this with another mathematician in the 80s at Cambridge University named Robert Dawson. And Robert Dawson tried to build, with some of his friends at Cambridge, this non-homogeneous monostable tetrahedron. It was built out of lead and bits of bamboo. As far as we're aware, this is the first and only previous attempt before this year to make one of these. And if you read the recent paper that just came out a couple months ago that Robert Dawson is also involved with, it seems that that model from the 80s is long lost. That's the only other attempt and we no longer have it. Or so we thought. Until a couple weeks ago, well, it turns out it does still exist. It's been looked after by, unbelievably, a friend of mine named Colin Wright. He's still got it. And oh, I could give him a call. He can show it to me. Back inside. So Colin, you have the missing model.
Well, I have a missing model.
Got it.
I've spoken with Bob Dawson, one of the authors on the paper, and his memory is that there were actually two models. So I have one of them, which I have very cleverly put down somewhere. Here we go. And I have a milk bottle.
It's in a milk bottle.
With one of the models. And if I tip it out, let me just hold it up to the camera here. I don't know how well you can see that because it's a spindly little thing.
It's tiny.
Yeah.
So it's a tetrahedron in that it's got three edges and a vertex.
Yeah. So we created the vertex on the top and then three arms, which are made out of bamboo, splints of bamboo. And then the other three edges on the bottom and the interior are entirely missing.
Right.
So it's an implicit tetrahedron to reduce the weight as much as we could. And it doesn't quite work. I mean, this is one of the reasons why at the time we made the model. We thought this could be made to work, but we need something that's got a greater density to be the weight at the top. And we need to get the angles slightly better. So the angles weren't quite right. But if I put this down on a surface here and I bend the camera down, then you may be able to see the little spider-like thing that's sitting there. And then if I let that go, you'll see that apparently it rolls over.
Oh.
Like that. And there you go.
Now,
it
always ends up on that face.
Right, so it's only stable, it should be only stable on that face.
Got it.
But what happens is the model doesn't quite work. So when I release it from here, it rolls from, call this face A that it's resting on now. It rolls from A to B to C to D. So it rolls from A to B to C to D. But the model doesn't quite work. So what actually happens is if I allow it to roll slowly, it actually rests on face B as well. So the angle here... no, it's very unstable. Yeah, the angle here is almost exactly 90 degrees, and it needs to be more than that. It needs to be an obtuse angle with the mass outside of it. So if I just help that over there, which is a bit tricky to do, but if I just help that over there, then it goes boom, and it does the final one. But what happens is, if I release it from the initial position, it's got enough speed as it comes over here to carry it over onto the next face and then onto the next face.
Interestingly, what Colin just showed me from the 1980s Bamboo model is a system where it starts on face A, that's unstable, so it goes to face B, also unstable, tips to face C, unstable, all the way to face D, that's stable, we have our monostable tetrahedron, and that is what we now call a type 2, which, as you may have noticed, implies the existence of a type 1, because what they had in the 80s was not the only option. Imagine a tetrahedron that starts on face A, that's unstable, goes to B, that's unstable, onto D, which is stable, but what about face C? Turns out face C, unstable, also goes to D. So you don't have a chain going from one to the other. There's just two different ways to get to the one stable face. And the big breakthrough 40 years later was when Jurgo, Robert, Gabor, and Christina realized you can actually build both of those different types of monostable tetrahedron. This fantastic paper that came out a year ago. So this was a big breakthrough that did not hit the news. It was only when someone made one that it did. And spoiler alert, they made a type 1. In this fantastic GeoGebra file, also made by my friend Sam, she's really helped me out on this. Now here, ignore these extra lines. They're the supports that were eventually built in the physical one. So spoiler, but if this was a homogeneous tetrahedron, that's where the center of mass would be, and you can see on face A, perfectly stable. Look at that, right above the base. But this dark region, that's a different density region. And if that was sufficiently more dense compared to the rest of it, you can see here, there's its centroid, the center of mass, and it's just above outside the base. So in theory, this means by making one region a different density to another region, we can kind of pick any arbitrary location inside the tetrahedron and move the center of mass there. If it just happens to be right in there, that moves it far enough off that we can tip from face A to face D. Now in this case, face D is the only stable face, and actually B and C both tip onto A, and then A tips onto D. So it is a type 1. And this is the one that was most likely to be able to be made. You just needed to have one region here that was a different density compared to the rest of it.
The only problem now is the ratio between the less dense part of the tetrahedron and the dense part has to be at least 1,000 times. It's like 3 orders of magnitude change in density for this tetrahedron to work. So I thought, even though I won't succeed, I'm gonna give it a go. So I have 3D printed this tetrahedron. I had to print it in 2 different sections, and then I've glued them together. To make this bit heavier, I paused the print where I'd left a cavity, put in some metal washers, like not 1,000 to 1, but it's something, and then continued the print. And so while this won't properly write itself, it's still a completely adequate teaching aid. So I can show you that if I put the heavy face down flat, that is definitely stable. Now actually, while you're speaking about 3D printing, it's me, Business Matt. This video is sponsored by Bamboo Lab. They make the 3D printer we used to make that tetrahedron. So Business Matt, are you allowed outside? There's a very good point. And particularly when it's windy, it turns out I can be outside, but the longer we sit here, the angrier camera person Alex gets. Although if they're already angry, would you like me to just pass this to you? Yeah, why not? I'm sure Alex will make it work. Thanks!
I was able to take the coordinates from the mass paper, recreate it in Bamboo Lab, split it very easily into 2 parts that I could later glue together, and I could design the print with a hollow void and then set it to stop printing at that point so I could put in the metal washers. I could not have made this tetrahedron, which almost works, or this video if it wasn't for my Bamboo Lab printer. If you already have a 3D printer and you want to find some fun mass things to print without getting coordinates from a mass paper and turning them into an STL, which I do recommend, you can head on over to MakerWorld, where there's a huge range of models available. And I always like to print something someone has requested, which this time was from video producer Alianne, who wanted 2 of these phenomenal knot prints to use as fashion accessories.
Oh good, you've got it back. That simplifies things. Anyway, link in the description below. Okay, so you've got the heavy part here. If I put that down first, that is definitely stable. All three other faces should be unstable. And you can tell if like that, you can see if I line it up, this just sticks out. If that was heavy enough, it would cause it to flip up like that. And likewise here, if that was heavy enough, it would cause it to tip that way. So while this doesn't actually work completely properly, having it slightly weighted meant that I could have a play with it and kind of get a sense of the overall geometry and why in theory it could work. Although it was only in theory until very recently. Building this thing to actually work was an incredible feat, and I really wanted to see it for myself. And the lead mathematician, Gabor, said that he'd be very happy to jump on a call with me and show me. Oh, here we go again.
At last, I had a phone call with Gabor and his student Yurgo at the Budapest University of Technology and Economics, who started off by explaining just how precise and difficult the engineering behind this model was proving to be.
And to design this thing, you needed kind of theoretical insight, which we had. We needed some geometric ideas, which we added. You needed engineering ideas, how to design the objects, and that we had. We are both engineers, but you also needed technological insight. There are several technological tricks which we could never have designed, and the result is certainly depending also on the technology. It's not something we are happy to disclose any part of this publicly, but I still would not recommend it to try.
Along the way, they showed me how their research could be applied to future space mission landers, and I took the opportunity to show them what I had made. This is your tetrahedron.
Okay.
But I 3D printed it in 2 bits.
Yeah.
And then I paused the print and I put a whole bunch of metal just in here. So that's the bit that should be a lot heavier. Obviously, the center of mass is still way, way in the middle.
How does it behave?
Almost good enough. So if you give it a bump, a little nudge, it'll do it. Or if it's got some momentum, but you can put it down and it will just sit there.
Matt, can I say something?
Yes.
So I think that building the actual tetrahedron was a big step towards making it accessible to many people. But another huge step is what you have done.
Yeah.
Yes, this is an enormous step towards many people, because now they will see what is the difficulty, because this is not a bad attempt. This is a kind of a professional homemade stuff. Yes.
Yeah.
Thank you.
Yeah. So this elevates the whole story to a different, communication wise, it is in a different league now.
But then finally it was time to see the actual model they had built. Do you have the tetrahedron, the engineered tetrahedron?
I have a piece of good news.
Yes. Good.
Of course.
Yes. It's got a special box.
And
Oh, wow.
So would you like to see it tip?
Yes, please.
I think. Okay. So it can do this tipping to the stable side.
Yep.
From this face. Also it does one tipping. And it's the most
one more to go.
Yeah. The most interesting one from the biggest opposite, well, not, from the biggest face. How can I do it? So you see, when it does 2 tips subsequently.
1, 2. Very fast.
Yeah, it works very fast, which is a little bit deceiving. So it suggests that it's easy to do, but that's not the case. So
actually,
if it's working, then it is working fast. But if it
work,
Or
then
if
we
it
don't
doesn't work,
see
it doesn't very fast. So yeah, so it either works very fast or in no
Or
way
not at
in
all.
this gravity. Yes.
Can you put it back on the big side and turn it around so I can see where the center of mass is on that plate? So there's that
Okay,
just
so-
off the base.
Well, the center of gravity is somewhere around here, I guess.
Yep.
Uh,
And that's just above, just off
yeah,
there.
just off the big face, yes.
Oh, wow.
So, some, yeah. That's the trick.
That's the bit mine doesn't do.
Just one comment, which is probably obvious to you, that the more faces a polyhedron has, the easier it is to make it monostable. And this is the most difficult problem in this category. If you can do it with 4 faces, you can do it with any number of faces. And it was a mathematical challenge. It was a historical challenge, which we ought to convey. It was a good topic for his diploma. I think it's a lot of fun for many people. People just love it, and it does connect to the space industry, but not in a trivial way.
Yes.
So this object, for example, doesn't look monostable.
No.
But it is monostable, and whether it can be made monostable, it's a delicate matter of these angles. So we even think that if you can take a lunar lander and design it so that it is not omnistable, but it is stable only on 2 or 3 faces, you already win, because you can design it, the antennas, you can design it for just 3 cases and not for 10 cases.
So given the model that was eventually made was type 1, I did also ask if a type 2 would be technically possible.
Now, our intuition and computations show that if you want to build that version, you need a core which is heavier than the core of the sun.
So there you are. I guess doesn't matter how good the bamboo and lead was, it seems the type 2 model made by Colin and Robert back in the 80s never could have worked. So that is the non-homogeneous monostable tetrahedron made real. Will that be the biggest mass news of 2025? We'll find out. If anything else happens, send me an email. I'll look into it. So thank you for watching the video. If you're wondering where I've been this entire time, this is a landscape sculpture called the Cells of Life. It's at Jupiter Artland, a wonderful site with loads of art just outside Edinburgh. I've always wanted to come here, and I thought filming this video would be a fantastic excuse to come and visit in a tax-deductible manner. I'll have a link to it below. I'll also link to all the STL files I use for printing things out in this video. Thanks for watching. Bye.